In addition to big O, there are other two notations used in the literature of the analysis of algorithms. These notations are big omega and big theta. In fact, these notations are closely related with each other. For example, if f of x is big O of g of x, then g of x is big omega of f of x. To show you how these notations are related to each other, first we need to define their basic definitions. First, we write the basic definition for big O. The definition is f of x less than or equal to c multiplied by g of x for all x greater than k. We will label the constant c c1, as you know that the relationship has two functions and two witnesses. Now, if we just reverse the inequality, so we write here f of x greater than or equal to c multiplied by g of x, and we will label the constant as c2 for all x greater than k. Then the notation that we will use for this definition will be big omega. And now when we combine them both together, so when you combine them together, we will have f of x, which is bounded between here, if you look at that f of x is less than or equal to c1 multiplied by g of x. So we write c1 multiplied by g of x. And also here notice that f of x is greater than or equal to c2 multiplied by g of x. So this will be greater than c2 multiplied by g of x. And of course, this should be true for x greater than k. And the definition now, the last definition, when we combine big O and big omega, will be called big theta. So big theta is in fact a combination between big O and big omega. So if we know that there is a function f of x is big O of g of x, and also we know that f of x is big omega of g of x, then we say that it is big theta, f of x is big theta of g of x. So here how we write the relationship, we say then f of x belongs to O of g of x. And here we write f of x belongs to omega of g of x. And here we write f of x belongs to big theta of g of x. To see how these two notations are related, let's consider the following example that we have solved before. We proved that 3n squared plus 6 belongs to big O of n raised to power 3 plus n. And we proved it by the basic definition, by the inequality 3n squared plus 6 less than or equal to 3 multiplied by n raised to power 3 plus n for all n greater than 2. And the constant or the constants for the witnesses were 3 and 2. Now divide both sides, divide both sides by 3. What you will get? You will get 1 over 3 multiplied by 3n squared plus 6 less than or equal to n raised to power 3 plus n, still for all n greater than 2. Now move this equation to the other side, and move this equation to the other side, and change the inequality symbol accordingly. So what we will get? We will get n raised to power 3 plus n greater than or equal to 1 over 3 multiplied by 3n squared plus 6, again for all n greater than 2. Now this is the definition for big omega, and this is the constant. So here we can say that n raised to power 3 plus n belongs to big omega of 3n squared plus 6. As a result, we can conclude the following. F f of x belongs to big O of g of x. Then we can swap these functions, but we need to change big O into big omega. Then we say that g of x belongs to big omega of f of x, and vice versa. What I mean is that if g of x belongs to big omega of f of x, then you can swap these functions but change this one into big O, so therefore the relationship will be biconditional. So now we are coming back to the basic definitions for both big omega and big theta. First, we have two functions from the set of integers or the set of real numbers. And if there are two constants, c and k, then first the basic definition for big omega, it says that f of x greater than or equal to c multiplied by g of x for all x greater than k. To see the relationship between f of x graphically, this is how the two functions are related. Remember, for big O, f of x is always in lower level than g of x. Now for big omega, it is the reverse. C of x is always on top of g of x. So g of x will be like a lower bound to f of x. Next is the basic definition for big theta. And again, if f of x is bounded between g of x with different constants, then we say that f of x belongs to big theta of g of x. So it should be now f of x belongs to big O of g of x, and also f of x should belongs to big omega of g of x. See the inequality. This part of the inequality is for big O, and this part of the inequality for big omega. Graphically, this is how we can represent big theta. As you notice now, in the middle we have f of x. It is bounded between c2 g of x and c1 g of x. So now c2 g of x is an upper bound of f of x, and c1 gx is a lower bound for f of x. So it is bounded between these two functions. When x goes to infinity, then it will never grow faster than g of x, and it will never grow slow than c1 g of x. Now for the big theta, we can divide the inequality into two parts, and we say equivalently f of x belongs to big O of g of x, and f of x belongs to big omega of g of x. So there is a strong connection, as we have demonstrated earlier, between big O and big omega notations. If f of x belongs to big omega of g of x, if and only if g of x belongs to big omega of f of x, and we have shown this by an example. Now, according to the graph we have, it says that if f of x belongs to big omega of g of x, then as x increases, then f of x grows no slower than g of x. It means that it will never go below of g of x. In other words, we say that g of x is an asymptotic lower bound of f of x. Now for big theta, as x increases, then f of x have the same rate as these two functions. So we say that they are asymptotically tight bound. That means it will never grows faster than g of x, and it will never grows slower than c1 g of x. This is how you look at the picture of the relationship between big O and big omega. Now imagine you have f of x, and you have a function on top of it, which is g of x. Then you can say that f of x belongs to big O of this function. Now also imagine you have a function, and there is another function g of x that is drawn in lower level than f of x. Then you can say that f of x belongs to big omega of g of x. In other words, when f of x looks down, every function below f of x will be part of omega g of x. And when f of x looks up, then every function in top of f of x will belongs to big O of g of x. Similar to big O, big omega and big theta are in fact sets. So as an example, if we have big O of n square and we have big omega of n square. So what is big O of n square? It is a set of families of functions that are in lower level than n square. And what is the set of big omega of n square? It will be a set of families of functions that are in lower level than n square. So all these functions in O(n) square, when you draw them, they will be below n square. And all of these functions, when you draw them with n square, they will be on top of n square. Now theta will be in fact the intersection. So the intersection between these two sets will be all functions that belong in O(n) square and big omega n square. This is how we can represent those notations as sets.